Measurement is our means of exploring quantities in science. When we look at measurement, measurement is a way that we can quantify our data. The units that we use in measurement are generally arbitrary units that we've created, but the things that we will be measuring are real things. There are three different basic units of measurement. We have the English system, the metric system, and the SI system. We can define a measurement as a count, a definition, or we have a way of arriving at units, rather, quantities, as a count, a definition, or a measure. A count is simply going to literally count a number of things. If I have 3 whiteboard markers sitting on a tray on a whiteboard, we count 3, and that gives us a number. We can also define values to exist. For example, we can define 60 seconds to exist per minute. That is a way that we have tabulated time. We have subdivided it into arbitrary units. Now, a measurement of something will be based upon our actually using some instrument to take a value. A count or definition will be what we call an exact number. Its value is exactly known. A measurement, though, is always going to be an approximation of the true value, and so will be considered an inexact number. Exact numbers have no uncertainty to them because we know their value exactly. However, inexact numbers are limited by the measurement that we make of them, and so will have uncertainty to them. The concept of uncertainty is based upon our understanding of an actual value and how that value actually plays out. So exact numbers are always certain. Inexact numbers are always uncertain. The measurement that we make of anything will be limited by the precision of the tool that we're using. We will keep the last digit after the final graduation, whatever calibration our instrument happens to be, and that will give us our level of uncertainty. So whatever the digit is after the last digit we can accurately measure gives us a level of uncertainty. So for example, if we take these two rulers, and let's say that these are graduated in centimeters, so that we have on the left a ruler graduated in half centimeters, and on the right a ruler graduated in centimeters. And both of these rulers are used to measure the stick. If we look at the ruler on the left, it looks like that stick is at the level of 5.5. If we look at the ruler on the right, we can't tell really where it is. We know that it's somewhere greater than 5, but somewhere less than 6. So looking at this, let's draw a line across to mark where the top of the stick is. It looks like the top of the stick lands right at the 5.5 mark on the left. So we could call that 5.50. We might say it's a little bit longer. It could be 5.51. On the right-hand side, we can't really tell, but we estimate that it's probably halfway between the 5 and the 6. Let's call it 5.55. So if we have 5.50 on the left, 5.55 on the right, those two different measurements are made of the same object, but the number of decimal places that we're keeping differs based upon the level of precision of the instrument. The instrument on the left is more precise than the instrument on the right. If we were to report using the right-hand ruler a value of 5.50, we would be incorrect because we are assigning a greater precision to our measurement than we are capable of with our instrument. Likewise, if we were to use the left-hand ruler and assign a value of 5.5 to the stick that we're measuring, we would also be incorrect because we are using less precision than our instrument is capable of. So when we talk about this word precision, a lot of people will tend to confuse or to use interchangeably the terms accuracy and precision. Now in science, accuracy and precision are two different concepts. Accuracy refers to the degree to which a measurement of something differs from its actual value. We can never know the actual value of something we're measuring. We're always going to be estimating it, which is the whole point in measuring it in the first place. So if we look at something which has, say, a true value of 2.349, if I measure 4 different times a value of 2.349 and I arrive at the results 2.348, 2.347, 2.350, and 1.129. The first 3 measurements that I made are very close to the true value. We would say that these 3 measurements are accurate because they reflect to a great degree the actual value. Now there is no way for us to know that actual value, but by taking multiple measurements here, we see based on our progression that the likelihood of the true value lying somewhere in the order of 3.49 is high based upon the way that our values have come out. Precision, on the other hand, reflects the level of uncertainty in a measurement, which means kind of the limit to our significance in our instrument, or a difference in the measurements. If I take several different measurements and those measurements disagree with one another, that is a difference in their precision. So if we take these these similar values here, we'll take 2.349, 2.350, 2.347, and 1.149. So we'll take these four values. The first three values are relatively close to one another, so we would call them precise. But the last value is different, so we would call it imprecise versus the first three. Looking at accuracy and precision, another way of explaining it is by kind of a graphical representation. If I took a target and I were to shoot at a target, this first picture demonstrates a series of shots which are precise. They are all close to each other. However, they are far away from the bullseye, so they're not accurate. The second diagram indicates an accurate shot. We hit the bullseye. We hit the exact value, so we're accurate here. This third picture is a series of shots which are both accurate and precise because they're all close to one another and they have hit the center of the bullseye. We've hit the target we're shooting at. This last representation represents a series of shots which are neither accurate nor precise. Now when we're making measurements, there will almost always be some introduction of error into our measurement. Error occurs in two different forms. We have what we call random error, which is error that generally skews data uniformly around an average value. We have the true value and our data fluctuates away from that true value, either up or low, but tends to stay around the true value. Things that can cause random error are things like unpredictable fluctuations, like fluctuations in temperature, fluctuations in pressure, things like flaws in our experiment, or human error. Systematic error, though, is the second type of error. This tends to skew data either high or low. All the data points will be high, all the data points will be low. Generally, systematic error comes from inaccurate calibration in a machine, or something like if I had a balance that had dust on it, the dust would add mass to that balance, and so my measurement would be imprecise or inaccurate. If we have impurities in our chemicals, that would also alter the values that we're getting. So all of these would skew our data in a systematic form. Multiple trials of any experiment tends to reduce random error because we can look at a series of trials like we did a moment ago when we were looking at those different measurements. If I only took one measurement and it happened to be the one which was very off, I would have no way of knowing that I'm differing from my true value significantly. But if I take multiple measurements and most of them agree to a high level of precision, but a few may be different, I can get a good idea of where the true value lies, and I can tend to eliminate random error based upon that. Systematic error can be eliminated by calibration. If we look at our instrument, make sure it's properly calibrated, make sure everything's properly cleaned, make sure our chemicals are of high purity, all of these can help to eliminate systematic error in an experiment. Now when we look at experimentation, usually both precision and accuracy are involved in the numbers that we're looking for, the quantities we're trying to get out of our experiment. And so because of that, we're going to want to be very careful in dealing with error in our experiment. Significant figures are what we call our means of keeping track of important data points in a quantitative measurement. All measurements will convey specific information. The digits in my numbers that have meaning are significant. Those digits which have no actual meaning are insignificant. So we have some digits will have meaning and some digits which will not have meaning. Digits with which have meaning are called significant digits or significant figures. We call them sig figs to abbreviate, and we have to look at our significant figures and we assume that our significant figures are correct to the first estimated digit in a number that we are measuring. So if I take a measurement in a lab with an instrument, the first digit that I have to estimate based upon the precision of my instrument is the limit of my significance. So a significant figure will show the level of precision or uncertainty in my measurement. Looking at how to track significant figures in numbers which we are presented or presented in data, there are several rules. The first rule is that all numbers which are not zero, all non-zero numbers, are significant in a number that is reported. So the number 7.314 has 4 digits that are not zero, and so has 4 significant figures. The location of the decimal point in a number is independent of the significance of those values. So the number 7.314 and the number 73.14 both have 4 significant figures. In a number, any zeros which exist between non-zero numbers are considered significant. So the number 60.052 has 2 zeros that exist in between non-zeros. Both of those zeros are considered significant, and so we have a total of 5 significant figures. Any number which has trailing zeros, which are zeros that occur after the last non-zero digit, will be significant if there is a decimal point in the number. So the number 4.70 has a decimal point, and its trailing zero is significant, giving it 3 significant figures. The number 100, as written in the second part, is lacking a decimal point, which means its trailing zeros are insignificant, and therefore it only has 1 significant figure. The last 100 written has a decimal point, and so because of that, both of its zeros are significant, and there are a total of 3 significant figures. In any number, leading zeros, that is, zeros that exist before the first non-zero number, are considered insignificant. So the number 0.0032 has 3 zeros before the first non-zero number, all of which are insignificant, and so has only 2 significant figures. When we look at exact numbers are considered to have an infinite number of significant figures. When we look at inexact numbers, though, the only number of significant figures that we can report are those which are based on the precision of our measurement. We will report only significant digits, but we would also need to make sure that we do report the full significance we allow. So we can only report significant digits, but we do need to report all significant digits we have available.